Hi, Shalin.
दो ही पहुंचे क्या अभी तक हम लोग?
I don't know whether students know also or not.
मैंने तो अपनी क्लास को भेजा था उनको.
हाँ, I think the dean sent it. और लोगों ने भेजा था.
नहीं मैंने अपने एक सेक्शन को मैंने ही भेजा था. इन द सेंस सेक्शन मतलब ये जो सेक्शन डी जो है.
Okay.
बस मैसेज आया था डीन का कि उनको भेज दो.
अच्छा. Today? आज?
नहीं पहले दोनों को एक साथ भेजा था ना दोनों.
हाँ.
27 और 29 को लिख.
Correct.
गेस्ट भी नहीं आए क्या अभी तक?
नहीं, he hasn't come. Hi, Prince. Good evening, Murthy sir.
So we are joining one after another.
Yeah. Good evening, Devi sir.
Hi, Sanjay.
How are you, sir?
I'm doing very well, Sanjay. How are you?
Good, sir. Good. Nice to see you after a long time.
Good to see you after a very long time.
Yeah. I think we met at Triple IT. After that, we didn't meet.
Yeah. Triple IT was the last time we met. I know. Yeah, that was a long time back.
Yeah. So, sir, welcome to IBS for this session, virtual session.
Thank you. Yeah. It would have been so much more better if it was in person, but nowadays everything is virtual. So.
Yes. So, sir, we have some faculty members on the Zoom call, and students will be watching on YouTube.
Sure.
So we'll start at 4:30. I think it's 4:30 already. So I'll start with your introduction and then hand over the proceedings to you. You can share your screen and go ahead with your presentation, and we'll take the questions in the end.
Sure.
I will moderate the session, so I will check the questions in the chat box and I will ask you.
Okay, perfect. Am I clearly audible, Sanjay?
Yes, you are, sir. Yes, you are. Okay, sir. So let me introduce you. So good evening and welcome to this session on big data. I am very happy to welcome Mr. Debi Prasad Banerjee to this session. He is Senior Vice President and Head Data and AI Practice at Wave Labs. He has built his career at the intersection of business and technology, incubating companies, building practices and growing businesses in large organizations. Over the last 2 decades, he has managed large customer portfolios and delivered on strategy and consulting assignments for customers across the globe. At Wave Labs, Debi leads our AI practice, building it into a key differentiator for the company. He also plays a significant role in building our business in India and Asia Pacific region for all our practices. In his most recent experience as Chief Strategy Officer at Niche AI, a startup in the artificial intelligence space, he was responsible for strategy, business, and customer advisory teams. Prior to this, he has worked in many large consulting and technology services organizations like PricewaterhouseCoopers, Cognizant, Wipro, etc. He used to manage customer relationships and deliver large-scale projects to clients in BFSI and telecom industries. Debi has studied advanced strategy at IIM Calcutta and also holds a bachelor's degree in engineering from BIT Ranchi. Again, sir, I welcome you. I hand over the proceedings to you. Please go ahead and make your presentation. Thank you, sir.
Thank you, Sanjay, and thank you to IBS and all the faculty members. Thank you for having me. It's a great privilege to be talking to all of you and your students. And I'm very happy to be here today and to share whatever little I have known and learned. I will share my screen and use the presentation. So let's see. Is my screen visible, Sanjay?
Yes, sir, it is. It is.
Okay, perfect. So good afternoon, good evening, everyone. Actually, it's 4:30 already, and all of you are in India, I'm assuming. We are so used to talking to people in all the time zones. So yeah, that's part of our job. So once again, thank you to IBS and all the faculty members and Sanjay for having me today. Today's topic is big data and its application, and I'm here to provide an industry perspective. So before we jump into the presentation and take a look at what big data is and how it is applied, wanted to start with a couple of disclaimers. So the first disclaimer is that by no means I consider myself an expert in big data. I am at best what you would say a practitioner or a user of big data, and the intention today is to share some of my experiences as we have traveled this journey, done a lot of different customer implementations, seen some use cases, and to provide you with a perspective on how not as such what big data is and the theoretical aspects of it, but how it is used and how it is benefiting the industry, both in terms of the progress that it has helped us achieve today and also the potential that it has in the future. The second disclaimer is that I am using a lot of theoretical building blocks, which Sanjay has been very kind to share with me. And that is because I thought it'll be good to start with some fundamentals and build upon that. And also it becomes easy to cite examples or provide insights on how some of these sometimes abstract or difficult to understand concepts get translated to the industry or to the real life, right? So I'll be starting with some basic definitions and what big data is and things like that. Hopefully, I'll be able to give enough examples on the way to keep it alive and interesting. And then we will talk about some case studies that we have implemented as part of Wave Labs. And then at the end of it, we can take questions, and hopefully we'll be able to give you an end-to-end view of the whole industry. So at Wave Labs, I head the data and AI practice, and the third disclaimer is that I've been looking at big data from a AI machine learning perspective a lot, which is again one of the primary usages of big data, which is analytics. So we do a lot of work on analytics and machine learning. Though there are many other uses of big data, there are many other ways big data is used and consumed, and we will probably touch upon some of them. But oftentimes you will find my examples or my experience a little biased towards analytics or machine learning. But that's just because that's the largest slice of the big data industry. So with those three large disclaimers, let's dive in. So we'll start with the basics. And we always start with the definition, right? That's what the good professor said. So what is big data? So again, here's a definition quoted from Wikipedia, a standard definition. But the important thing in this definition is basically the first line, which says it's a collection of data set which is large and complex. Did someone have a question?
No, sir.
Sorry, I thought I heard something. Sorry. So yeah, it's large and complex, and I think that is the crux of the entire theory behind big data. That it is basically very, very large and very, very complex, and that is why it makes it difficult to use traditional data processing methods to process big data, right? And if we understand how it becomes so large and why it is so complex, then that would help us understand how to overcome the complexity and the magnitude, and then how we can effectively use it for our needs, right? The challenges that we currently deal with big data start from capturing. So when you have a very large volume of data, how do you capture it? And then, of course, once you capture it, you have to curate it, which means basically cleansing it, transforming it, making it usable, and then finding a way to store it. Again, not just storage, but also retrieval. When we say storage, we also assume retrieval is included. So storage and retrieval with efficiency. And then, of course, you want to do something with the data, right? So you want to search, you want to share it, and then you want to analyze it, and you want to draw visualizations on top of it. So all of that, it should be possible to do, and it should be possible to do it in an economical and easy way, right? So that's where the challenge and in terms of complexity comes. So let's look at some of the things that do make big data big and which make big data complex, right? Why is it so big, and what makes it big, and what makes it complex? So this is the classical definition. Most of you may have heard about it. We'll look at each one of them turn by turn, and we'll try to see what makes the three V's, and maybe we can look at some examples as well as we go down. But essentially, three V's is a very standard way of defining big data. Some people have add a fourth V also, and we'll touch upon that. But primarily, it's volume, velocity, and variety. We will take a look at each one of them. But just to summarize, when you have large amount of data and it's coming at you at a very high velocity, very high speed, a lot of it is being thrown at you, and they're all of different types, different categories, different formats. That complicates your problem. That makes your problem, thrice as more difficult. So one is the volume you have to deal with. You have to deal with the velocity, so you have to do it quickly, and you also have to have mechanisms by which you can attribute the different varieties and take care of the different varieties so that no data is lost, right? So when all three of them are switched on together, and you have to deal with that is where the problem comes, and that is where the traditional applications, the data processing or data management applications have had difficulty, and that has given rise to the research and development and eventually new technologies which have enabled the fueling and the growth of big data. So the picture on the right side here also gives you kind of a timeline idea. So if you look at the arrow in the middle, you see it's we had ERP data earlier, which was your basic company-wide system of records for production, manufacturing, and then we had the CRM, which had the customer data in it, and that was pretty much what the world was in the early late 90s. And then the web came in, the internet came in, and then we started looking at opening up the enterprise and getting different types of customer interactions through the web, and that generated a lot of different new type of data. And then eventually we have the mobile, and we have the social network, and we have the sensors, which is your largest contributor of the data today. And when all of that come together, you have the true realization of the three V's, right? And that is where eventually we have come to in big data, where we are talking of the sensors, the users, such as you and me interacting over our phones and our mobiles, and of course, all the other transactions that are going on in the cyberspace outside of enterprises, plus the traditional enterprise interactions are anyway there, right? So that's what makes it all very large and extremely complex. So let's talk about volume. Some statistics here, just to give you an idea of what we are talking about. So the picture on the top talks about 2009-10 to 2020, last 10 years, and we were not even 1 zettabyte in 2010. So we are now looking at close to 44 zettabytes. So this one says 35. There's the figure in the below which says 45 zettabytes. So that's the volume of data that we're looking at. And that's the rise.
Devi sir, can you wait for a minute, please?
Sure.
Sir, I'll just mute everyone, and then you please unmute yourself and then start. Yes, sir, please go ahead. Sorry.
Okay, can you hear me, Sanjay?
Yes, sir. Clear.
Okay, great, thanks. Right, so we're talking about the growth from less than 1 zettabyte to close to 45 zettabytes in a span of 10 years, right? And that's the kind of growth we've seen. And if you project that, then uh, we are uh, we are going to be, looking at a data which is at a volume of data which is probably we don't even have the right measurements in this day to measure, store on and report on that volume. So that's the kind of growth we're looking at. But just to give you some facts, 1.7 megabytes is created every second for every human being. So as we are talking, going through this presentation, close to 2 megabytes of data is created every second for all of us. And this includes the digital trail that we leave behind and all the interactions that we have. Um, it's just mind-boggling. And 1.7 megabytes may seem like a small number, but when you multiply that by 7 billion people, and that is every second, it very quickly becomes very, very unmanageable. So that's the volume of data we are talking about. And where is this volume coming from? Where are the different what are the different sources? So this is again an interesting slide I found somewhere, which talks about basically expands that 60 seconds. So I will give you a few seconds to look at this and consume this. Some of you would be using some of these services. Not everybody uses all of these, but most of you will be familiar with them. 168 emails are sent every second, every minute. Can you believe that? 168 million emails every 60 seconds. So that's the kind of volume of data we're talking about. And all of this is potentially usable data. All of this is potentially searchable. We can draw analytics from it. We can use it, and companies are using it. So this is the kind of volume we're talking about, and this is growing. And we have to have tools and technologies and platforms to manage this volume. So this is where the volume comes from. Another quick example of the volume, CERN, which most of you know about, has several experiments. The largest one is called the Large Hadron Collider, LHC, and that alone, the LHC alone generates 90 petabytes of data a year. And that is, so you have megabytes, gigabytes, terabytes, then you have petabytes, exabytes, and then you have zettabytes, right? So that is what we were seeing in the earlier slide. So this is 90 petabytes of data a year. And all the other experiments, which are considerably smaller than LHC, produce about 25 petabytes a year. So that's the kind of data that is being generated. And all of that is being stored and used and consumed in some form or the other. And that is just one experiment. Another experiment that is generating humongous amount of data is the human genome experiment. All of you would have heard about it, and we have decoded the human genome, and now we are able to utilize that and do a lot of different things. But that project alone had generated humongous amount of data, and now that everybody's getting their genome sequenced, and you can actually pay $25 or $50 or whatever and get your genome sequenced. Each time you do that, hundreds of gigabytes of data is getting generated. Right? So there are these scientific experiments as well, which are generating tremendous volume of data. So that should give you an idea of the volume of the kind of data we are generating every day. And I did not even talk about the enterprises. The enterprises are generating data internally. We were just thinking about the world in general, people, and our interactions with each other. Of course, the enterprises are continuing to generate data like they used to do, and in a much more voluminous and much more faster fashion. So that's always there. The second word, the second V is variety, right? So which is also sometimes called complexity. So where is this variety coming from? Very, very simply put, the type of data that we are able to now produce and consume has increased many folds. Earlier, while we may have been able to produce many different kinds of data, we were not able to store and consume them. Our best bet of storing and consuming was structured data, right? Data that was you could store in tables. transactions, those kind of data. So that is how the world was. When we look at 80s, 90s, we are talking of data that is generated by computers, stored into tables and used from those tables for generating reports or taking whatever action. But all of it was basically what we call structured data today. Then when the internet came and when different forms of communication like emails came, we realized that we also can store regular English text, not only English, any other language text data. And eventually we started developing tools, machine learning, intelligent tools, which could read and decipher and analyze that data. So suddenly all of that unstructured text data that was considered unusable or useless suddenly became usable, right? So all your emails, all the documents that you write, every single word that has ever been written is now available as text data in some server somewhere or the other, and that is now accessible, and we can process that, we can make sense out of that. There are tools which let you do that. So that data then became usable, and therefore it came within the fold of big data, where that became another dimension of the data that we use. And then there are the semi-structured sources, as we call, which are again computer generated sources, which are used for information exchange between computers, like XML or JSON, where you can have text data embedded into a structured form, where there is a structure or there is a logic on how the data is stored or sequenced. But inside that sequence, you can have unstructured text data. That is why they're called semi-structured. So now we have a lot of information exchange between computers or between sensors to computers. Basically, machine-to-machine communication happens in a semi-structured data format, and all of that is again stored and usable. And then we have something called a graph data, which is also, in a way, it can be considered as a semi-structured or, yeah, it is a semi-structured data, where basically this is another way to represent the interactions. It comes from graph theory and the way we store, analyze, and work with the interactions between two individuals or two entities rather. The good example is maps, GPS systems, geospatial systems, and the biggest one is the social network. Your Facebook, Twitter, Instagram connections, and the way those things are processed and structured uses the graph query language and graph data. And then last but not the least, the biggest culprit of data volume is streaming data. So if you ask me today, the largest volume contribution comes from streams. And we'll see how that happens, and some of it you can imagine. IoT sensors, right? IoT sensors, industrial IoT, audio video streaming. If you just take those three for a minute, those three are ubiquitous, right? They're everywhere. You may or may not know, but your house probably has so many different types of sensors. I mean, your phone is like a walking bag full of sensors. There's so many different types of sensors that your phone has. Some of you may have systems like Alexa or smart devices like smart TVs, etc., smart fridge. So all of those are the consumer sensors, but much bigger world of sensors lies outside, is what is called the industrial sensors. And all of these are constantly generating data, streaming, and these data is getting stored. So most of the machines that are being used in manufacturing today are either automated or semi-automated. Even if they are older machines which are not automated, they have sensors embedded on them. And these sensors are constantly 24/7, every few seconds, streaming the health of the system. And all of this data goes into the cloud, is analyzed, and things like predictive maintenance is a very big industry right now that entirely depends on the sensor data. Sensor data is also used for doing real-time activities like rerouting traffic or so many other things that happen on a day-to-day basis, which we don't realize, are ultimately coming from sensor data. For example, when you are traveling, you're driving and you're looking at Google Map and you say, okay, this road is looking jammed, I should take the other road. All of that is basically your phone beaming out information in small packets. In this case, your phone is the sensor. But just to understand that, your phone is basically beaming out information every second which is being collated by a server, made sense out of, and then all that, people who are traveling on that road, all of their information is coming together using their GPS coordinates. Everybody is co-located, and then there's an algorithm which figures out that there's a jam on this road because nobody seems to be moving, right? So that is possible because your phone is there acting as a sensor and beaming out the data. So that's just one example which helps us understand, but the actual world of sensors is very, very large, and that is what is causing one of the largest explosions in the data that is being processed and handled today. And then last but not the least, the scientific and the medical data, which is also a huge impact on the overall contribution to that type of data. So scientific data, we saw CERN, we talked about human genome, but so many other types of scientific data that is experiments that are happening in every field of science is constantly being captured, either on site or through sensors, or sometimes through satellites, and all of that data is beaming somewhere into the cloud. Some server is storing it, and then it is getting analyzed. Medical data is even bigger because now the medical data is not restricted to hospitals and places of treatment. Medical data is now coming from all of us. We are all, most of us are basically walking sources of medical data. If you're wearing a Fitbit right now, you're actually generating what we would call medical data, right? It can count your heartbeat, temperature. It can do a lot of things depending on what kind of device you have. There are specific medical devices which patients are using, which constantly monitor your heart rate. Like people who are suffering from arrhythmia, for example, or some other heart conditions, they have small devices which constantly beam out data, and there's an app on your phone which monitors that. And this is becoming more and more proliferated, right? So you have shoes, shirts, pants, trousers that you can wear which beam out, which have sensors which beam out data, and all of this is being sold under the area of wellness. So you are basically saying that I'm buying these devices because now somebody else is going to monitor my health and tell me if something is going to go wrong, right? So it's like predictive maintenance for human beings. But that's another huge source of medical data apart from what gets generated in the industry, in the hospitals. So what is it about variety that makes it difficult, or that makes it why would variety be one of the reasons, one of the 3 V's that we would consider? Simply because if you take any of these data, or well, most of these data in isolation, they can give you maybe limited amount of information, or they can give you limited amount of analytics. The power that we harness and that we generate today from big data comes from the fact that we can correlate, we can link these different types of data that are coming. And that is the most important thing I want you to take away from this V, from variety, which is the power of the analytics comes from our ability to link them, join them, or mathematically speaking, correlate them. If you're able to correlate them, then you're able to draw trends. You're able to draw different conclusions from it. And that is why the variety is important. And that is where processing different variety of data gives us the power to make better predictions or deeper analytics. Just to reinforce that point, this slide shows a typical customer, you, me, anyone, and all the interactions that we have in today's world. So if you see, all of us have social media accounts. Most of us do. We are interacting with the financial system. We have credit cards, bank accounts. There's entertainment. I'm sure most of you watch Netflix or some form of OTT entertainment. There is gaming. There is your interaction with the companies, with the industry. So SAP, IBM are basically systems of records here, which could be anywhere. Your hospital, your bank, or anybody could be using historical data on you. And then, of course, your purchase patterns are, so the moment you take a membership or the moment you sign up for something, that company will start storing data on you, right? So all of this is what is commonly known as the digital trail, right? And some of this is explicit, Like, for example, you have to have a bank account, or you have to have a credit card to generate those transactions. So they're explicit. Some of them are implicit, where you open a social media account and you only sign up for so many things, or you know so many things, but you don't realize that there are hundreds of other different varieties or categories of data that is being captured under that one accounts, right? So some of it, quite a lot of it is explicit. Implicit. Some of it is explicit, right? But all of this put together creates what the industry calls as a single view of a customer. So imagine if you're able to get hold of all of these data points and you're able to correlate them, what kind of power it gives you, what kind of insight it gives you into a human being. And if you have difficulty in imagining that, the best example that I can give you is what happened in 2016 US elections. There was a company called Cambridge Analytica. Most of you would have heard of Cambridge Analytica. It is eventually closed down. And Cambridge Analytica was using a lot of different sources. Most people think they were using only social media, but they were actually using a lot of different sources, primarily social media. And at that time, they claimed that they had 5,000 data points, 5,000 unique different data points for every American voter. Okay, I'll say that again, 5,000 individual unique data points for every American voter. That is the kind of power that they had. And that correlating that data, correlating all of those data points gives you tremendous power about knowing a person enough to influence his or her decisions. Some of it is explicit by showing you ads and banners and etc. Some of it is implicit, subliminal, playing certain ads or playing some kind of background music or showing you flashes of images. So there are different techniques, which is way beyond my capability to understand. But essentially, that decision to do that comes from correlating those 5,000 data points per voter. And we know that the effect was real, and we saw what it could do. So that is what a single customer view is, and that is what variety of data gives us, and the ability to correlate all of them. All right, now the third V, velocity. So velocity is basically how quickly the data is being generated and how quickly the data needs to be processed and stored. And earlier, if you go back 20, 30 years, maybe, a data would be generated, let's say, when a transaction happened, right? And a transaction would happen certain number of times in a day, like when you go and interact with the system, you buy something or you withdraw money or you make a purchase or whatever it is. So there were discrete transactions that happened, and that is when data was generated, right? When an employee joins a company, that's an event. When an employee logs into the office every morning, that's an event. So there are these events which would generate the data, and they would happen at discrete intervals. Now, what is happening now is that interval has basically come down. It has come down to minutes, seconds. In some cases, it has gone down to less than seconds, milliseconds. We're talking of sensors which sometimes generate data at sub-second level. And that is useful because the events that they're tracking are changing so fast. But essentially, that is what velocity is. It basically means that the data is being generated and transmitted, and it needs to be processed and stored with the same speed at which it is generated. Otherwise, you get backlogged. If you don't process it as soon as it comes, then the next one will arrive. And if you're still processing the first one, then you get backlogged, and very soon the system will break down. It's very easy to imagine that it will not stand up. But more importantly, if you are not able to process the data quickly once it arrives, you will not be able to make real-time decisions. And a lot of the systems today we take for granted are based on real-time decision, real-time analytics. And that is only possible if you are able to build systems which can consume the data which is being generated at such high velocity. So we'll take some examples here for you to quickly understand. One of the examples that I have put here is from a project that we are doing, and we'll talk at length about it a little later. But let's start with that. The third one, security and surveillance. So this is also part of a project that we are doing. It's for a law enforcement agency in US and Canada. And but I'll give you a slightly different view of that example, and we'll cover that example in the case study. So imagine that you are imagine that you are in the US and you are in a mall, and this is a very real use case. This has happened several times. All of you would have heard about it. But essentially, you are in a mall or in a public place where there are a lot of people, and there have been incidents, as you know. Somebody walks in with a gun and opens fire, right? And dozens of people are killed. This has happened so many times in schools, in churches. It happened in a large gathering in Las Vegas where and 30, 40 people died. So essentially, these are public places. Given the gun laws of the country, people can walk in with weapons and this can happen. Now, there are systems being put in place. If you take a mall, for example, where somebody walks in with a weapon, or even if the weapon is not visible, if let's say somebody walks in who's on the FBI wanted list or the local police wanted list, there are cameras, the regular security cameras, which are looking at people as they're walking in, and they're able to detect bad actors. They're able to detect somebody who's in the most wanted list, on a terrorist list or on a police
Devi
watch.
sir, one sec, sir. Can you speak up, please? Volume is slightly low, sir.
Okay. All right.
Thank you.
Yeah, let me know. Sometimes this mic acts up a little. So let me
Yeah.
know. Just it.
Carry on, sir. Sorry.
That's okay. So there are these systems which are able to detect people, bad actors. They're able to detect weapons in real time, and they're able to alert local security, law enforcement agency. And the hope is that before any incident happens, these bad actors will be caught or disarmed. Now imagine if this information is not processed in real time. If there is a 2-minute, 3-minute, 5-minute, 10-minute lag in processing this, right? Then the whole point of having such a system would be lost, because you want to catch that person as soon as he walks in. You're able to detect his face or the gun or whatever it is, and you're able to match it, alert, and take a decision that yes, this is a person who needs to be apprehended or taken down. So the whole point of that is to be able to do it real time, right? Another example I'll give you from my own life, where we were working in a startup prior to my current job, and there we were building a system for paying tolls, right? So all of you travel through cars and you pay tolls, right? And we have this new system now where it automatically detects your vehicle, and it kind of deducts the money from your account. That just came in, but this was 2-3 years back when this system was not FASTag system was not implemented. You would have to stop and pay toll, and there was a lot of fraud that happened in the toll plazas. People misused, they would take less money and put more money and things like that. So essentially, there was fraud happening, and there were money being pilfered. So one of the solutions that we put into place was to look at the video camera data coming in from the video camera and determine what kind of vehicle it is and how much money they should be paying. So if it's a truck, they pay 500 rupees toll. If it's a car, they pay 300, and so on and so forth. So that system was real time. So if you're unable to detect what vehicle it is and how much money should be charged, and you're not able to match that, by the time the guy goes away, you can only do an audit later, but you are not able to prevent that, right? So in order for that system to work in a preventive mode, it had to be completely real time. So these are some of the examples of real time decisions where there's money at stake, there's human life at stake, and then there are some more innocuous ones which are very useful, but they're not as nobody's going to die if for example, if you don't do a promotion. But then for the advertisers and the retailers, the promotion is very, very important. So when you walk into a mall, and it knows from your phone, from your GPS, it knows you're in the mall, it is able to give you on real time, immediately it's able to give you the deals on that mall, right? So that also works real time, and it also happens to use this part of the big data infrastructure, which is basically ability to process data immediately, right? So this has got important implications. Late decisions is equal to missed opportunities, and in some cases, late decisions could be lethal. It could lead to human life as well, right? So that is why processing data in real time is very, very important. Some of the ways that these data is being generated, but like I said, the biggest one that I would point out here is the sensors. They're everywhere and they're generating data constantly. And these sensors are, some of these sensors send in data every second or every few seconds. Even though the payload is small, payload meaning the amount of data sent in each packet or each ping is small, but it quickly adds up, right? You have hundreds of these sensors sending data every few seconds, even if they are in a few kilobytes. Very soon they'll add up per device or per sensor per month. We are talking of at least megabytes. And then if you think that there are millions, literally hundreds of millions of these sensors, we are easily talking petabytes to exabytes of data being generated from these sensor networks. So that is where the largest velocity data is coming. Okay. Another important thing to mention here is the scalability. So when you have high velocity data, obviously your volume adds up. So the third V impacts the first V very, very quickly. So therefore your systems, your big data systems by definition need to be scalable. If your systems are everything but not scalable, then it's not a big data system. Then you're in trouble because it's going to saturate very soon and everything is going to crumble and fall apart. Right? So it's very, very important for these systems to be scalable. And that scalability is one of the reasons why big data is so popular today, and it was not so popular 20 years back, because 20 years back, we didn't have a very scalable infrastructure for this. And that scalable infrastructure, as all of you know, is the cloud. And we'll talk a little bit about it, but it's a good time to pause and think about big data being, cloud being an enabler for big data. You also have on-prem big data systems today, but then the real scalability comes from having the big data system on the cloud, because that's where you have, theoretically, you have access to infinite compute and infinite storage. So it's going to cost you a lot of money, but that's a different point. But you at least have access to that scalable infrastructure. And one of the reasons why big data is popular today is because it is cloud is able to provide that scalability. All right, so if you look at this slide, this just tries to capture what we were talking till now. So you have all these different types of data sources coming at you, and all of this needs to be put together. And the ultimate aim is to improve the overall customer experience, improve your and my experience as we go through this digital life that we lead today. So some of the like the more innocuous ones, like I said, product recommendations, the ads that you see at home on the browser or on your TV, to when you walk into a mall or the airport. Some of the ads are getting more and more custom and more relevant. The movies that you watch in Netflix, there's extremely intelligent Netflix recommendation engine that takes into account your behavior and your past experience, past preferences. But some of the most serious ones, for example, preventing fraud online, or even when you're swiping your credit card somewhere, preventing fraud as it is occurring, rather than the fraud happening, you reporting later, and then they will find out what it is and remit your money back. There are systems now which can detect fraud as it is happening, and it can stop the transaction from going through, right? Which means they're constantly monitoring every transaction, as the transaction happens, not just the entire transaction, but it basically follows through with the transaction, and it constantly matches with your spending pattern and other things. So that's a big advantage, or something that is very important to the end consumer. Safety and security, we talked about. Real-time threat deterrence is going to become is already a big agenda item. And then there are more useful things like map, GPS, traffic updates, things like that, which we all need, and some of us depend on it. And all of that happens through real-time analytics and decision making by very large complex systems running somewhere, but they materially impact our life on a day-to-day basis. And all of this, everything that I described till now, all of this is enabled because we have compute systems which can handle large volume of complex data. In other words, big data. right? So whatever we've discussed till now, the examples that we gave in the 3 V's, ultimately, the way to think about it is that whatever impact it has on your life, it is only possible because we have systems, we have processes in place which let us consume, process, store, and analyze this data, sometimes in real time, and draw decisions out of it. And using those decisions, using those analytics, decisions are taken, and that decision then impacts our life. Most of the time, we want to think it is positive, but in case of Cambridge Analytica, for example, not so positive. But nevertheless, they are decisions which impact our lives. Right. So that's how you would correlate the importance of big data in our lives. Right. So I talked about the fourth V, right? Veracity. So what is veracity? Veracity basically talks about the quality of the data, right? So a lot of this data, I don't want you to go away thinking that everything that is generated everywhere is useful, valuable data. That would not be right, because a lot of this data that is generated, that we talked about, is junk, useless, or not useless, but not usable. And many times it is inconsistent, erroneous, like sensors malfunction all the time, incomplete. Sometimes there are delays and the data becomes useless. So there are a lot of these, there are a lot of reasons, some technical, some business, some because of the platform itself, which renders a lot of this data unusable, right? So when we talk about the 4 V's, the fourth V basically brings in veracity, or the correctness to the data. So we are only able to consume and use the data that is correct or accurate in that context of that problem, which is why we remove a lot of inconsistency. And the word cleansing or cleaning, data cleaning, you will hear repeatedly, is very important, where you take out all the junk, all the noise, as it is called, and then you use only what you need or what is correct, usable. So that is the fourth V, which is very important filter to apply before the data becomes truly usable, right? So big data, for our definition, from a generation perspective, it is being generated from all over the place. So all of that is the velocity, the volume, and the veracity, and the variety. That is on the generation side. When it comes to the usage side, you put the veracity filter. You take what is good, what is important, what is usable, and then you use it. Right. That's how you would think of the big data world. Right. So that kind of takes care of the definition and the 3 V's, but hopefully we've been able to cover a little more than just definitions. Now, how do we harness big data? How we tap into the potential of big data? Again, a little bit of history lesson. OLTP, OLAP, most of you would have heard, and that is how the world was. OLTP is online transaction processing, has been there forever, ever since IBM started making mainframes and selling them in the 60s, 70s. We have online transactions. And online here does not mean the web. Online means happening on a computer. And then you have OLAP, which is analytics processing, which has been there since the 90s. And we know it by the name data warehousing. And then the associated word is business intelligence. So data warehousing, and then using the data warehouse to generate what we call business intelligence. In those days, it was more like MIS reports, right? So basically, slice and dice the data in simple ways and report on them. So that was the use of OLAP systems. Now these OLAP systems started growing, and eventually they somehow transformed or morphed into what we now call real-time analytics processing, so RTAP. And this is where you need the big data architecture and also the infrastructure, very, very important, to be able to realize a RTAP system, right? Otherwise, if you don't have the big data processing, and we'll talk about that quickly, but if you don't have that, you will not be able to do real-time analytics processing on a OLTP or OLAP-based system, right? There are system-level barriers you will hit, which will not allow you to do that kind of work, right? So therefore, the advent of big data architecture and the infrastructure to support it has led to real-time analytics processing. And the next avatar of that is what we now call data science or machine learning, where we are taking that to the next level, and we are doing a lot more interesting things with it, not just analytics, but we are doing forecasts, predictions, recommendations, simulations, a whole bunch of different things, which was not possible earlier without having the the variety and the veracity of the data that is available today. This is how the data landscape has changed, and this is typically when you talk of big data, you're talking of analytics and data science. Though it is important to note here that the CERN data, for example, that we talked about, 95 petabytes a year, that is very much a big data problem, and that is big data. Though CERN will not be interested in doing a lot of analytics, right? CERN will be using the data in different ways. They're looking for exotic particles or whatever it is that they're doing. They will not be running analytics algorithms like we do in the industry. So there, even though the infrastructure is the same, you still have, for example, Hadoop-based systems, but the way they use it would not be for doing real-time analytics, right? A lot of the sensor data that is coming from the weather stations all over the world, and that's humongous, another thing we forgot to touch about, but the weather stations around the world generating sensor data about temperature, pressure, humidity, etc. Those data points are not being used for doing analytics. They're being used for creating complex weather models, which tells you your forecast, which tells you what happens next week, which tells you when the next hurricane will come, and so on and so forth. None of those are analytics processing. But then again, that's the part of big data that we are not touching upon today, right? We are touching upon today is the more industrial, the analytics processing part of big data, which is what when we in the IT industry, in the regular consumer industry, when we talk about big data, that is what we refer to. We don't refer to the complex mathematical model to find the next black hole. That is also big data, but that is not what we talk about. Just to clarify that. Right. So so the big data processing model itself has changed. And earlier, the generation of data used to happen in a few places, but the consumption used to happen everywhere. Right. So this was the model before. Like a bank would be a place that data would get generated. A manufacturing unit would be a place where data would get generated, right? But and that would get consumed by so many different downstream systems. But today, data is being generated everywhere. Like I said, all of us are generating data. There are sensors everywhere. So essentially, it is completely disaggregated, completely federated. Data is being generated all around us. It's a matter of finding the right way to tap into it, and then again, it is being consumed by all of us, right? So that is a key difference on the model, and therefore, to cater to this, we have to design systems differently now. So the systems earlier could be more monolithic, for example, because the data is being generated in one place. You have a monolithic system to deal with it. Now the data generation is completely federated. It's all over the place. So now you have to have systems which are again completely federated and completely modularized, which can process the data locally and generate meaning out of it, right? So that leads to the way data gets processed. What is driving the big data? Like I said, this is the field that I personally work in, and most of the work in big data in the industry happens in this space, which is driving analytics, statistical and predictive analytics. Most of it is real time because the applications are such that the more real time it is, the better business value you get from it. So a lot of the growth in big data is coming from the demand for doing real time analytics, right? So takeaway from this slide would be that real time analytics requires a lot of big data to be available, and that is one single reason why more and more big data systems are being implemented and used on a daily basis. Earlier, of course, business intelligence, if you just want to compare, it was mostly about, like I said, MIS, so data mining and ad hoc querying and reporting, mostly structured data sources, less of analytics, very less real time, right? So those are the two things that have changed, and that is what is pushing systems to, yeah, this is an interesting slide. So here we have tried to put some timeline as well, though it may not be exactly accurate, but it broadly kind of fits in the bottom if you see the timeline. So we had your OLAP systems and your data warehouses where you would process your data and you would report on it, and then you wanted speed. right? So you wanted them faster and you wanted them to scale out. You wanted to process more data. So we have RDBMS, we have in-memory RDBMS, we have tools like SAP HANA, Tableau, which have in-memory databases which allow you to do faster querying and therefore faster reporting. When you scale out on the processing side, that is how big data was born, where you start to process more and more data, and then we got into this whole parallel processing and distributed processing mode, and we'll talk about that a little bit very soon. And then once you had these two in the 2010s, you had the big data systems where you could scale out and process large volume of data. You had in-memory databases, which lets you give you a lot of speed. Then you wanted scale and speed again. So you wanted to scale out further. And then that's how the Facebook way of doing things, the Google and Facebook way of doing things, which is using graphs, for example, graph query language and graph databases started to come together. And eventually what we are seeing now is what I call pipelines. And data pipeline is a word that I use very frequently in my daily life. And data pipelines are nothing but a combination or an ensemble of different components. And all of them could be different technologies. You can pick the best of breed technology for each of the components, and you can put them together in a pipeline, which gives you an end-to-end processing. So all the way from data being generated, capturing the data, processing, storing it, and using it by the downstream systems. All of this can be put together in a pipeline using state-of-the-art systems, and it gives you the best of the breed solutions, right? And that's again something that we'll talk about. So in order to realize the pipeline, in order to realize any of the big data things that we talked about, what do you do? What are the tools available today to you? And if you look at the landscape, it looks very ugly. The slide is not very clear, but that's not what I'm trying to say. What I'm trying to say is that it's very, very confusing. And there are a lot of different technologies and systems and vendors and tools, and everybody claims that they have the right solution. So how do you break it down as a practitioner, as a big data engineer, as somebody who's going to be working with big data? How do you break it down? So what I have tried to do here is talk about the core technology instead of talking about tools. Just talk about the core technology that enables the big data, that has enabled the big data revolution. And most of these systems and tools that you see, they are somehow or the other built using the fundamental building block or underlying big data technology, which is called Hadoop. You may have heard of this. I'm sure all of you have heard of this. So it's a project from Apache, okay? And it's basically a set of open source software utilities, and it has a family of things that it came with, and they keep adding to it. So this family itself has grown quite a bit, but I wanted to stick to the basic ones which are most used and which are most useful. So Hadoop, under the Hadoop project, under the Hadoop umbrella, Apache came up with a bunch of open source utilities that enable the big data processing. Now, before you look at this, you have to think, what is the underlying technology? Why was it not possible to do some of these things before? And to understand that, we have to look at the origins of Hadoop, right? What does Hadoop use underneath? And I will not go very technical underneath, but it uses a technology called MapReduce. Again, most of you may have heard of it. And MapReduce is basically a programming model, or it's a technique, and it's basically, it allows you to do distributed parallel processing on a cluster of computers, right? Very, very simply put, it allows you to do distributed processing on a cluster, which means you're harnessing the power of more than one computer, more than one CPU, and you are able to distribute your workload across different CPUs. Essentially, it's a realization of distributed programming. And once the MapReduce framework, or the way of doing things using MapReduce, that whole ecosystem was created, Hadoop was just a realization of that. It is just a commercially available realization of that MapReduce package. You can use MapReduce in its core form also. I think many people uses it. Google uses it in some way. Uber and Tesla use it. But most people like us in the mainstream industry, we would directly use Hadoop. We would not bother with MapReduce because Hadoop implements MapReduce. So this MapReduce technology was available. It is not that it is very new, it's been there. But what Hadoop did is that the guys in Apache, they took this and they put a wrapper around it and they made it basically easy to use. And they called it Hadoop. And that gave us basically a way to store and process large amount of data, because underneath it, it distributes the computing across a cluster. So you're not restricted to one CPU anymore. You're not restricted to running a small amount of workload on one CPU, because that CPU can only handle so much. Now you have multiple CPUs. You can break the workload, you can parallelly distribute it, and you can run the workload, bring it back and recombine. And you have your solution, or you have your response, right? So Hadoop lets us do it. And once they cracked this and once they created this, what we know today as HDFS, Hadoop Distributed File System, is basically a storage platform. And Hadoop Distributed File System is the generic name, and every cloud provider has their own version of HDFS. Every software vendor, large software vendors have their own implementations or their own names for the HDFS file system, but underneath it is all using Hadoop, that technology. Right, so that was important. So I spent a little bit of time on it, and the rest of the tools that you see here, Kafka, for example, is a streaming system, right? So anytime you have streaming data, IoT, the sensor data I talked about, you would need something like a Kafka. Again, Kafka is the core product from Hadoop. Different providers have put wrappers on it, and Azure calls it Event Hub, and other people have different name for it. AWS calls it Kinesis, but essentially Kafka is the core streaming platform. And of course, Spark is very important to mention here. So Spark is a real-time processing engine which sits on top of your HDFS, your Hadoop storage. And Spark lets you parallelize your job. So whatever programs you're writing to process the data, Spark basically lets you parallelize that and run it as a parallel load. Right. So just to give you an example, if you have 100 million records, right, 100 million records. Now that's a very, very large workload. 100 million records processing on a regular computer will take minutes, if not hours, like several minutes. To break it down and to get real-time results on those kind of workloads, you need to process it parallelly. So that's where the power of Spark comes in. It uses exactly the Hadoop infrastructure, breaks down the workload, gets it executed across the cluster, puts it back together, and gives it to you in very, very fast real-time mode, right? So that's what Spark does. And then, of course, there are Hive, Splunk, HBase. These are various things that are tools that have evolved, which help us store, analyze, and process data in different ways. This slide tells you the core implementation on what each of the cloud guys call it. So sometimes you'll hear these names, but essentially they are nothing but HDFS. In AWS, it's called S3. In Azure, it's called ADLS. And in Google Cloud, it's called GCS. Ultimately, they're all implementations of a distributed file system, which follow the Hadoop principles, right? Similarly, Kafka is called Kinesis, Event Hub, Cloud PubSub, right? So this is just to show you that underlying there's the same technology, but there are the wrappers provided by each of the cloud providers. But broadly, this is the ecosystem that most big data engineers will be working with, right? Most of them will be working with one of these stacks or a combination of these stacks. So this slide here essentially breaks down to this as the underlying technology, which enables all those tools. And these are the core tools of each cloud. So just to break that down in a way that it's easy to understand. All right, spend a minute on, so cloud, we had referred to cloud earlier. As we said, it basically gives a scale out, and without cloud, we would not have had big data, simply because you do not get the scale. You cannot keep adding servers and compute power required to process the kind of data we're talking about. So if we did not have cloud where you could scale out your compute and storage at a click of a button, having a big data revolution like we have today would not have been possible, right? So now cloud computing is everywhere, and we think of it ubiquitously, though the big data paradigm, as I showed here, can be implemented on-premise. You can buy servers and you can install Hadoop distribution from a company like Cloudera, Hortonworks. They give you Hadoop distributions. You could deploy that and do it. But then, you would run into that scale problem sooner or later. So typically you would do it on the cloud, and it has become synonymous. When we say big data, we typically mean cloud. I'm going to skip that and probably skip this as well. Benefits are quite obvious for doing in cloud. Economies of scale, obviously resource management. You don't have to worry about your data center and things going down. You don't have to set up a new data center or a new set of servers every time you want to add more data. You just request for more resources. So scaling is faster, easier. It's easy to manage cost. It's highly reliable. And of course, it is sustainable because it is owned by somebody else who just does that for a living. So it's, you can always depend on that. Right, let's spend some time on the about next 15 minutes on the data engineering pipeline and the case studies. So data engineering is a term that is very common nowadays. And the way I look at it and the way we break it down is that we talk about data engineering is being comprised of data management. And this is the pipeline that I talked about. And we'll spend a minute on that soon in the next slide. Basically, a pipeline to capture data, aggregate it, clean it, process it, store it, and use it for downstream application, right? So this whole pipeline is what I call the big data management. And that is the core part of data engineering. But then once you've done all this with the data, what do you do with it, right? You just can't have data sitting there doing nothing. Then there's no use of the data. So the important thing is the business use, how the business is using it and how you're deriving value out of it. And that's where comes in business analytics and visualization. It could be regular old-fashioned visualization, where you're not doing much analytics on it, you're just reporting on various dimensions. Or it could be analytics, advanced analytics, where you're using statistical tools to derive different kinds of correlations and other things. And then, of course, the last but not the least, when you start applying more sophisticated techniques on the data, like regression, and you start looking for meaning, and you start doing forecastings and predictions from it, and that's when you enter the world of data science and machine learning, right? So big data is basically the engine that feeds this whole machine learning and AI revolution. Without big data and without these platforms and these pipelines, we would not have the data science and the machine learning revolution. So this is how a standard typical data pipeline looks like. It's an oversimplified view, but just to call out all the components, you have your sources on the left, structured and unstructured, semi-structured. We talked about it in the beginning. All the different sources, the variety of sources. They all come together and we write custom data aggregation subroutines. There are tools available here. We could write your custom routines depending on what data you're getting. And then you aggregate all of this data and you put it together into a lake. Typically, a lake will be an HDFS, Hadoop-based system, as we talked about, right? So this is where all your data sits in large NoSQL format. NoSQL is basically not an RDBMS, right? It is basically a columnar database or basically a file system. You can think of it as a file system. So, so these are all HDFS implementations, right? So that's a lake. It could be a S3 lake on AWS, or it could be a ADLS lake on Azure, or it could be a standard HDFS Hadoop implementation at your own data center. But ultimately, that's what we call the lake. A lake is nothing but a very large storage. And then from there, we pick up the data and we clean it. A lot of cleansing is required. I talked about the veracity step, right? And even after the veracity step, there is general cleansing that is required. Simple things like removing nulls, deduplications, making sure that phone numbers are 10 digits and so on and so forth. So basic cleansing is required. You do that, and then you do transformations, whatever transformation your business demands. And then after the transformation is done, you store it back into another lake. We have not shown it here, but essentially after the transformed data is also stored in the same lake in a different, let's say in a different folder or wherever, a different instance of the lake. And then what do you do with it? You can either do advanced analytics and generate dashboards, which your business can then use, or you can use the same data to do the data science, machine learning, data science and insights, data insights. And eventually that also gets consumed by the business in the form of dashboards. If they are decision-making systems, then they also get routed into your enterprise application where they are used for powering decisions. Like, for example, a system that detects a threat, right? So the output of that engine will go into maybe a 911 call in the US, for example. So that's how it gets consumed. So this is your entire data pipeline. Just a deeper view of that. Again, I don't want to spend too much time on it. It shows the different steps, the data ingestion. That's the aggregation step we talked about. So you connect to sources, internal, external, social media, outside, pull all the data, and then you put it together using connectors and custom adapters. And then you bring it together into a raw storage where you have a positive and a negative storage. Again, these are little technical words, but essentially it means that you not only get the good data, you also get the bad data, and you keep it together. And then you do the scrubbing and cleansing. And then you do the transformations. During transformations, you could do advanced transformations, use processes like principal component analysis, PCA, or exploratory data analysis, EDA. These are all tools which allow us to do very, very complex transformations and analytics on the data. And then we can create intelligent sinks. It's an option. It is not always necessary, but as an option, we can create intelligent sinks where the specific data required by specific types of cognitive engines or analytics engine can be stored for easy access. And so typically, this is how a data pipeline gets constructed. This is how big data gets consumed. So big data is coming from the left, as you can see this in this funnel, flowing through all of this, eventually getting consumed by an analytics or a cognitive engine, and then impacting the end user in whatever form. Could be a dashboard, could be an application. But this is the life cycle or the life pipeline of a big data system. Right. Let's spend a few minutes on some real life examples, case studies that we have been working on, that my present company has been working on, and I have been intimately involved. And these are all, I've picked 3 today, but all 3 of them are very, very interesting. And I have tried to pick the 3 to show you the different types of big data and the different types of uses, the different aspects of our life that it touches, right? And some of that we've already covered and touched upon. I will use these to elaborate a little more on them. And this is the first one. So this is for a online streaming company. All of you watch Netflix, Amazon Prime, whatever it is, your favorite. So this is for Sony. So Sony in the US is trying to launch a online platform much like Netflix. They already have a platform, but essentially they are trying to build a better platform, let's say. And what we did in that project is to build an end-to-end data pipeline, right? This pipeline that we talked about. Essentially, we tried to build something like this for this project. But what makes it interesting is the sheer volume of data, and also this is a good example. All the 3 V's, right? That's one of the reasons I chose it. So let me give you some idea of the volume. So any online platform that instance of the player. And when we were doing this project, they had 100 million total users. 50 to 60% of them were active, right? So we were talking of close to 250 million events being generated per day, even before they launched it. Like in their current state, when they launched it, they expected more customers. But even with the current customer base, are watching Sony TV, right, or Sony broadcast. This adds up very quickly. If you look at the monthly figure, it is 7 billion events that are coming in. And 200 million, 50 million events coming per day. If you divide that by total number of seconds, it'll give you an idea of how many events are coming in per second. And this is just the health data. This is just the heartbeat data coming from the app, which is playing the movie. Now, inside this payload, there is a whole bunch of information about not only who you are as in a user, it has information about the content, it has information about the system on which it is playing. It's a complex payload, fairly complex payload, right? Then you combine that with other systems. So on the left here, if you see, we are getting this video events, which I talked about. Then you're getting subscription and you're getting application data, right? So there are non-player events that come in. And you're not actually watching a movie, you're just browsing. Each of those clicks, each of those events, each of those mouse movements are captured. So your system exactly knows you're going from which screen to which screen, whether you're moving from a TV serial to a movie, or you're moving from a documentary to a movie. It knows every single detail, right? So those are the non-video part of the events, which is the app data. That gets combined with a lot of different other types of data that comes in. So this gives you the variety, the different types of data that we combine together. The velocity is that 7-second payload, 7 seconds for every player, which means at any point of time, there are several a few hundred thousand events coming in at any point of time. And then your volume is basically coming from the velocity itself. That is giving you the volume. Plus there is the content, which has also got considerable volume. So all the content, all the TV programs, movies, whatever is available, all of that. Now you put all of this together, and we used Event Hub in this case, which is, if you remember, is an implementation of Kafka by Microsoft Azure. And we process all this data. We use a system called Databricks for processing, and we eventually store it into a SQL database. And then from there, we run analytics engine on it. And in the first phase of the project, we generated phase of the project, we started looking at prediction and forecasting. So if you have, what are you likely to watch, and then you make recommendations based on that, right? So this is an example of an extremely large big data system where the end consumer is consuming a video, but the data that is being generated and processed is basically a text-based payload, right? So again, 7 billion events being handled per month. And this is easily going to get into petabytes in a matter of months. So there's very important considerations on scalability and on storage. The next one that I want to talk about in a little bit detail today is for a marketing company. This is a predictive analytics system that we had built. So this basically deals with marketing data, where this deals with ad placement, right? So when you watch Google, when you go to Google or any of the Facebook, Twitter, anything, you see all these ads, right? So those are paid for, and those are placed by companies, and they're all paid for. And there's a very complex system that is running, which decides which ad gets shown at what time. Manages that system of placing ads for their customers. And they have close to 160,000 customers, and each of them place hundreds and thousands of ads on a daily basis at different mediums, Facebook, Twitter, etc. So again, the volume of data that we're talking about is tremendous here, coming from all those 160,000 people placing hundreds of different ads in different mediums. All those ads have their own payloads, they have their own characteristics, and that needs to be brought together, processed, and analytics generated on top of it. Now you have to understand that these ads keep changing through the day, so they are all sensitive to time, to geography, location, events, etc. And they all have dynamic attributes. So it is not just capturing the data, it is also capturing those attributes dynamically each time an ad is getting placed, and capturing them, and then later using that to analyze the performance of the ad, what the ROI was. If you placed the ad, did you get any click on it or not? So that the customer knows that if they spend $1,000 on placing an ad at of a pizza shop at 10 p.m. in the night on Facebook, did anybody click on it, and did any pizza get ordered or not? So based on that, the marketing head will decide whether he wants to spend another $1,000 tomorrow on it or not, right? So it's an important business decision to be made. So the data needs to be captured, analyzed, and processed, and there is a time limit here. Like I said in the beginning, some of these reports are sensitive to the few hours to days where decisions need to be made and the ad placements need to be changed. The next level is where you change these algorithms and you basically feed this data into ML algorithms, which then make decisions on behalf of the marketing executive. So he doesn't have to sit and decide anymore. There's an ML engine that is running, which makes recommendation that, okay, if you want to maximize your gains from this ad, you should place it at 12 p.m. in this location for this much duration, right? So you basically make algorithms which are smart enough to do that. Now, in order to do that, the amount of data that you capture has to be significantly higher, right? So this company, they had to put together additional data capture fields that they were not capturing earlier in order to enable a system like this. Again, we are talking of like hundreds of terabytes of data being generated every month. I'm sorry, every year for this company, and they're not even the biggest. They're like a medium-sized company. So if you look at some of the large media houses, we are talking of truly talking of big data, like petabyte level data. And this is the last example, and this is probably my favorite. We talked about it in the beginning. This is basically a project that we are doing for a surveillance company, where we are doing live threat detection, right? So I mean, this kind of epitomizes the use of big data in real time, right? So video feed coming in from camera from any place. It could be your house, it could be a public location, it could be your office, it could be a college campus, anywhere you have video cameras. That feed is coming in live 24/7. It's getting uploaded to the cloud, and it's getting processed, and it is constantly looking for threats. It could be weapons, it could be knives, guns, explosives, or it could be bad actors. It could be anything that is out of place. So this is and here just to give you some idea, typically a HD camera that we have, most of the cameras today are HD, and they have 35 to 40 frames per second is the speed that we take, and they are 1080 pixels minimum HD capacity. So 1080 pixels, 35-40 frames per second. That's the kind of video data is being generated, right? So every second 40 frames, which means 40 JPEGs, which are 1080 pixels, are being generated, and that's the volume of data that you are getting. And imagine in a school or in a public place, or even in your college, if you think about, you have tens or maybe even hundreds of these cameras, right? So a security system implemented in a place with, let's say, 100 cameras would be uploading 100 into, even if you take 30, 100 into 30 JPEGs, frames of 1080 pixels every second, every single second, right? So that's the volume, and that's the velocity of data that is coming in from here. And then obviously you process that, you use AI algorithms to process that, and then you generate the output. But all of this would not be possible if you do not have a highly efficient pipeline like this. The fundamental building block of any of this is to have a pipeline like this, which lets you process the incoming data in an efficient way, allows you to do the transformations, and then only you can use the data for doing analytics or for doing data insights. If you do not have this, then your data is not usable. And if your data is not usable, then it's just data, right? It's just big, and it's just data. It's not the big data that we know and that we love. right? So that's what I wanted to cover. We have about, I think I overshot a little bit. Sanjay, you said 15 minutes, but I think we have
That's
about
okay,
10
sir.
minutes for the question and answer. But I want to stop here and just want to reiterate that it was a pleasure to have this opportunity. And I'm sure I did not cover a lot of things. I'm sure I left a lot of loose ends, but I'll be happy to answer any questions today. And in the future also, you can get in touch with me via Sanjay. I would be happy to give any answers or help you out in any way. Thank you. Thank you.
Thank you, Devi sir. It was quite a comprehensive presentation on big data. So Professor Kalyani has a couple of questions. Professor Kalyani, feel free to ask those questions. Okay, I think, okay. Before that, let me ask a couple of students' questions.
Sure.
First question is, what are the skill set, or what is the skill set required to get into this field, big data and AI, to an MBA student?
Okay, good question. So MBA student, I'm assuming when you are getting into big data, so there are two ways to do it. One is purely functional, or where we are not actually implementing big data systems, as in writing code and implementing it, but we need functional experts who are very knowledgeable about the domain in which big data is implemented. For example, a security use case requires people who understand that domain. A banking system requires domain experts of that domain. So that is one way where if you're functional and not very technical, you could still be working with large data systems or decision systems. But I'm assuming your question is more on the technical side. So on the technical side, one of the core skill set that is required is, we talked about this slide here, any of the Hadoop-based technologies. So Spark is a very good skill set to have. Python as a programming language is very good. It's called PySpark, which comes along with Spark, Python flavor. So that's a good place to start, Python and Spark. And then work on any HDFS or Hadoop-based distributed system. It could be on Azure or AWS or Google, does not matter. But Python and Spark and some HDFS system would be a good place to start. Apart from having a very good idea of SQL in general, SQL queries and databases and data in general, which I'm assuming most of your students will have, Sanjay. Adding Spark, Python, and Hadoop to it should make it fairly easy to get into this.
And sir, one more question related to this. How necessary is for them to understand the technical details of big data?
Yeah, so that is the first part of the answer that I was trying to give. So if you're getting in from the functional side, where you're working in a banking industry and you know a lot about the banking data, you need not become. I mean, you don't need to know Spark or Python and write programs to implement big data pipelines. You could come in as a domain consultant or as a person who understands this domain. I'll give you a simple example. If you're processing fraud, right? You're building a big data system to process fraud. Now, if I go in, I don't know anything about banking transaction data. I don't know anything about the 20 fields that come in when you swipe a credit card. So how will I understand which data to look for? I may be very good in implementing Spark. I may know a lot about correlations and regression algorithms. But what am I going to regress? Should I regress this field or that field? I don't know that, right? So that knowledge has to come from somebody in the industry. So there is a very important and a very role that is not fully appreciated, where every big data project, every machine learning project requires deep understanding of the domain. So you could approach it from that way if you don't want to get too technical and don't want to learn about the implementation part of it.
Right, sir. Thank you. So Professor Kalyani's question, she's asking me to ask the questions. So first question is, in the real-time processing scenario, what do you do when the data itself is changing, right? The data is streaming, you are doing the analysis, but the data itself will change. So how do you handle such a situation?
When you say data will change, I'm not sure what that means. Basically, are you talking about the format of the data changing?
Format of the data and the basic information itself will change, right? For example, I'm watching something now, and then suddenly I change my mind and I start watching something else. So there is a hodgepodge of different data points that are going into your system, which you are processing. So how do you handle that?
So the way we handle that is essentially when you create a payload. Let's say we are talking of a sensor grid that is sending data. So when you're
Mhm.
coming, getting real-time data, it could be like like a video processing. The example that I
Correct,
gave about
correct,
Netflix.
correct.
Or if you take a sensor grid that is sending out pressure, temperature, humidity kind of data, what we do is when we define the payload of that data, we
Mhm.
define the payload in such a way that it has all possible fields that could be generated by that sensor grid or that could come out of that video feed.
Okay,
Now, the payload will be designed in such a way that most of the fields will be nullable, right? So you will not expect all the fields to come at all the time,
okay,
but you design the payload in such a way that it covers all possible data generation patterns or ways it can be generated. And then when you construct that, when you convert that into a JSON, for example, you will have all the fields available. Most of them will be null, and then depending on which field has come, you could have a processing done based on whether a certain field is available or not available. In fact, you can write triggers to look for certain fields, where only when certain fields are available you would act. Otherwise, in fact, that's a very real use case where you get a data from a sensor grid and you look for a certain pattern or a certain combination of fields, and only when all of them are true or available, you take an action. Otherwise, you don't. Right. So
okay.
that's typically how we define the payload and we process the payload.
Okay, one more question from Professor Kalyani was, do you use the entire data set? Do you use the census or do you take a sample and do the analysis? When you say statistical analysis, it is done on a sample, right? So
So
in this case, I assume that the entire data set is taken into account for analysis. What's your view on that, sir?
right. So two different scenarios. One is if you're using a machine learning algorithm, for example. So when you are
Mhm.
training, if it's a supervised system, or even if if you're using something simple like a regression, when you are building the system, you would like to build it with as wide variety of data as possible, right? So that it can cater or it can work with all extreme scenarios as well, right? If you build your system with a subset, then it will basically not work, or it will give you incorrect results when deviations happen, right? So your idea would be to take as much of the data set or as much of the variation as possible um, when you are building or training, when you're building your model, or when you're training your AI system or analytics system. In fact, sometimes when we do not have enough variety, we inject variety. We use data augmentation, and
Okay,
that's a very common technique, and we use it all the time to make sure that we augment the data to cater for all different varieties. I'll give you a simple example that when we are training for visual data, like the video surveillance data, we blur the images.
okay,
Even though we have good images, we blur it. We introduce something called a Gaussian blur, which is a very simple blurring technique. We blur it because in real life scenario there could be fog, there could be water vapor in the atmosphere, and the image could be fogged or blurred, and then my system will not work, right? So we introduce noise, we introduce conflict, we introduce different scenarios by data augmentation if it is not present. But in a sensor grid, typically all these things are there. We do remove unwanted noise, like we do remove broken sensor. If a sensor value is supposed to be 0 and 1 and I'm getting 5, then obviously I want to remove it. So those kind of filtering we do, that's the veracity part. But within the tolerable range, we take as much data as we can get to make the system as robust as possible.
right, sir. So as a player in this industry, what is the kind of competition you are facing on a day-to-day basis?
Competition is everywhere. Competition is very very. So there are competitions from different types. I mean, there are obviously larger companies who have more people, more skill set, and all that. But I don't think that's the question. I think the question is more about how this is evolving and what kind of tools and technologies are coming in. So one of the sources of competition that we are facing is there are a lot of startups who are both here in India and abroad, especially in the US, US, who are building systems which are based on this open source stack that you see on your screen now. This is the core open source stack, right? So you can use the stack and you can build various types of systems which are very specific to certain industries or certain use cases. And you make these end-to-end tools, or you make a system which is, does 80-90% of the job out of the box. And when that happens, it's very easy for a customer to go and buy a system like that or lease a system like that and not have to build it from scratch. So as a pure services industry, not only us, but everybody in this space, I think would be facing severe competition from a lot of new age companies who are packaging these solutions to very, industry specific frameworks or industry specific solutions.
Like the system integrators of your, is it?
Like the system integrators of your, yes, like that. And also some of these are also cloud hosted. So there is a very real business model where if you create a solution using an open stack and you host it on a cloud, it's very easy for you to charge a fraction of the cost and still be profitable, because you are then supporting several different customers, right, on the same cloud. So you are creating a system which can be installed once and used many times, and that is how you make your money. The only problem with that is that you get locked into that vendor, but there are many customers who don't mind that. As long as your service is good, they don't mind using a cloud-based, hosted cloud-based provider. And that is also a real source of competition for service-based companies like us who thrive on custom coding.
Right. So one last question and then I will let you go. So all these big organizations, they would have their own big data department or big data division, right? It would be very easy for them to buy out small players and work on their data on their own. So do you face that challenge, or is it not a challenge?
Yeah, that is also a challenge. So there are so talent is not as abundant as we would want it to be, right? So if there are people listening today who want to join this field, there is a lot of demand. That is for sure. Everybody is looking for good people, and we don't find good people. If you have industry experience, which many of your MBA students have before they come, that just makes it all the more better, right? If you have industry experience and you've done some work on big data side, then you are extremely valuable. So because talent is hard to get, anytime a large player finds good talent, they will hold on to it. There are a lot of buyouts that are happening in this space, and we expect a lot of consolidation to happen in the near future, because the algorithms, the systems are getting more and more complex, because the business use cases themselves are becoming more complex, and the number of people who are able to support and solve that is not going at the same pace, right? So that space is going to get a lot of attention. And in terms of demand and in terms of the message for people listening today, I think this is an excellent field to start and build your career on.
Right, sir. Thank you once again, Debi sir. It was a pleasure listening to you and interacting with you, and hope you also enjoyed the session. I'll be in touch and hope to see you in the conference that we are organizing.
Yes, I look forward to that, Sanjay. Thank you for inviting me for that. And especially for today's session, it was a pleasure. We do this in our own life. We go to office every day, we build systems, but sometimes, when we get an opportunity like this to share what we have learned, it is always a great pleasure.
So one more thing, can you share the presentation with us? Is it shareable with the students?
Yes, a couple of pipeline diagrams I think I'll have to remove, because those are specific for the clients.
Yeah. So please sanitize and send it to me. I will share it with the students.
Definitely, Sanjay. I'll do that.
Thank you, sir.
All right,
And
Sanjay.
good night.
Thank you. Thank you.
Bye,
Yes, thank you.
Thank you, sir. Thank you.
Thank you, sir. Thanks.
Yep, interesting. Thank you very much.
Thank you, and bye-bye.
Bye.